myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the today's lecture, we are going to solve some of the problems based upon what are the primary constants of a transmission lines in electromagnetic waves and transmission lines. So before going to solve some of the problems based upon this primary constants and secondary constants of a transmission lines, let me introduce first what are the primary constants and secondary constant. How will I express all the primary constants in terms of secondary as well as all secondary constants in terms of primary constants of a transmission lines. So first, an airline has characteristic impedance of 70 ohms and phase constant of 3 radian per meter at 100 megahertz. Then calculate the inductance per meter and the capacitance per meter of the line we need to measure. So an airline means for a free space transmission line we are considering as an example, and characteristic impedance is given. That characteristic impedance is represented with Z0. Generally, this impedance is to be measured in ohms and characteristic impedance need to be measured in terms of ohms, and its value is given as 70 ohms. And the phase constant means we are representing it with beta and is given by 3 radian per meter at 100 megahertz. Frequency is also given at high frequency, that is 100 megahertz. Then calculate the inductance per meter means L value to be measured and the capacitance per meter also to be measured. Right? So here characteristic impedance means characteristic impedance Z0 and the phase constant is given. Now from this, as we know that gamma equal to alpha plus j beta equal to, means if alpha equal to 0, that propagation constant gamma constitute only phase constant beta, right? As we know that characteristic impedance Z0 is given by means all the primary constants of a transmission lines, means resistance R, inductance L, capacitance C and the conductance G are called primary constants of a transmission line, and characteristic impedance Z0 and the propagation constant gamma are called as secondary constants of a transmission lines, right? So Z0 can be written as in terms of all the primary constants, then R plus j omega L by G plus j omega C. And the propagation constant gamma can be written as root over then R plus j omega L into G plus j omega C. Right? So by multiplying these two, Z0 into gamma, then we are getting the value as R plus j omega L. So from this, now to find Z0 into gamma, if you multiply, then R plus j omega L or Z0 by gamma becomes 1 by G plus j omega C. By simplifying these two, we will be getting the values for either inductance per meter or capacitance per meter, resistance and the conductance might be obtained. So before considering these two relations, we'll have some more simple formulas in order to find all the primary constants of a transmission lines. And the given one first. So as an airline can be, means an airline has a characteristic impedance like that he has given. So that airline can be considered as a lossless line, right? So for a lossless line, we are assuming sigma equal to 0. Then sigma, if sigma is to be assumed as 0, attenuation constant alpha is also equal to 0. As alpha 0, there is no loss in the signal, hence it is said to be lossless one or perfect transmitted line. Then since sigma equal to 0, hence R equal to G equal to 0. Why R equal to G equal to 0 means these two are the two power dissipated elements, and hence if alpha equal to 0, we are assuming R equal to G equal to 0 in that particular, right? So if you substitute R and G by 0 over here, see Z0 into gamma becomes j omega L and Z0 by gamma becomes 1 by j omega c. And as we know that Z0 into gamma means we'll have here in place of gamma what we have j beta, and that will be given by Z0 into j beta equal to j omega L, and from this Z0 into beta equal to omega into L is to be obtained. Or from this Z0 by gamma means j beta nothing but Z0 by beta equal to 1 by omega c. See, Z0 value and beta value is given, and omega is also to be given, that is angular frequency. We know that the formula omega equal to 1 by 2 pi f, omega equal to 2 pi f, and f value is given as 100 megahertz. From this, we will be getting the value as C. See here, Z0 value is given as 70, by beta value is given as 3 radians, which is equal to 1 by 2 pi f. F is given as 100 megahertz, 100 into 10 power 6 into C to be given. So we have to evaluate here capacitance C per meter. So to find C means C equal to 1 by 2 pi into 100 into 10 power 6 into 70 by 3. So see here, C is equal to 3 by 2 pi means 140. 2 into 7 becomes 140, and here 10 cube, and this becomes 10 power means 14 pi into 10 power 9 need to be obtained. So from this we will be evaluating the value of C, and C can be measured in terms of farad per kilometer. Why? Because throughout the length of the transmission line, that capacitance need to be varied. Okay, that's why C is to be measured in terms of farad per meter or kilometers in terms of, right? So now, similarly now to find L, see what we have here, Z0 into beta equal to omega into L. Now from this, what? Substitute here Z0 by, again same, what? Z0 by 70 into beta by 3, which is equal to 2 pi f, means f value is given as 100 megahertz, that is 10 power 6 into L. Now from this, L is equal to 70 into 3 by 2 pi into 10 power 8. 100 becomes 10 square, 10 square into 10 power 6 becomes 10 power 8. So then if you evaluate, if you simplify this one, then the answer is to be obtained, and this can be measured in terms of Henry per kilometer or term meters. Similarly here also the inductance is to be evaluated throughout the length of the transmission line, right? So this is the one of the method to measure the given parameters as either inductance per meter or capacitance per meter need to be evaluated. Or we will go for another formulas as Z0 is equal to root over L by C. Why? Because if we substitute over here R and G by zeros, then j omega gets cancelled, root of L by C is to be obtained, and Z0 must be here R0. Characteristic impedance is sometimes represented with R0. And as we know that beta for a lossless one, beta to be obtained as omega root over LC. Right? So by simplifying these two, R0 by beta equal to 1 by omega C. Now from this, C equal to beta by R0 into omega or Z0 into omega. So by simplifying everything, we'll be getting the final answer as 68.2 picofarad per meter. Okay. Then similarly, L is equal to R0 square into C. Now substitute or R0 value by Z0 value into the capacitance value to be obtained as or here as 68.2. Then it has to be expressed in terms of 334.2 nano Henry per meter. Right? We can go for either one of the method is the total one is like this. Then another method is to be by simplifying Z0 in terms of lossless as root over L by C and the beta value as omega root over. Then by multiplying 2 and by dividing those two, then capacitance need to be obtained as 68.2 picofarad per meter and L value need to be obtained as 334.2 nano Henry per meter. So here this nano representation is 10 power minus 9 and the pico representation is 10 power minus 12. So in both the cases 10 power minus 12 is multiplied over here and here nano representation, that is 10 power minus 9 is to be left, right? This is the way we have to, means if the secondary constants of a transmission line and along with the operating frequency is given, then we need to find all the primary constants in terms of secondary, means this two methods need to be followed. Next, one more. A transmission line operating at 500 megahertz, F value is given as 500 megahertz and has Z0 equal to 80 ohms. Characteristic impedance is given 80 ohms and the attenuation constant alpha is given as 0.04 Nepper per meter and beta to be given as 1.5 radian per meter. Now find the line parameters R, L, G and C. Right? So here in the previous case we have considered air as a transmission line, means air line means considered to be as a lossless one. There we have assumed for a lossless one sigma equal to 0, then alpha equal to 0, then R and G values must be 0. Now here along with the attenuation constant alpha, beta is also given. This is the case, this is not applicable. Now we will solve it in different way. That is, find the line parameters. Line means here transmission line parameters as R, L, G and C. So to find R, L, G, C values here and see RC equal to GL, means for a there are two different types of distortions less transmission lines we have discussed, that is lossless line and a distortionless line. So for a distortionless line here, the condition is to be given by RC equal to G by L, G into L, or R by G equal to L by C. The condition for distortionless transmission line is given by R by G equal to L by C. Or simply if we multiply these two, RC equal to GL or G equal to RC by L. Now from this, characteristic impedance Z0 is equal to root over L by C or root over R by G. Right? So why? Because for a distortionless transmission line, and if you substitute over here, Z0 is equal to root over R plus J omega L by G plus J omega C. Now it becomes R naught equal to root of R by G or sometimes root of L by C, which is given by, means that characteristic impedance Z0 is nothing but the resistance value to be as sometimes we use the notation as R naught also. And we know that this one is given as alpha beta equal to omega root over LC and attenuation constant alpha equal to root RG. So by separating the real and imaginary terms, means the propagation constant gamma equal to, in general, means it is expressed in terms of all the primary constants, then it will be given by R plus J omega L into G plus J omega C. Right? So by separating real and imaginary terms, means RG plus J omega RC plus J omega LG plus J omega into J omega becomes minus omega square LC as this way. Right? So as we know that gamma equal to attenuation constant alpha plus J beta, by comparing both sides real and imaginary, then attenuation constant alpha becomes root over RG, and then from this formula alpha equal to root RG and beta equal to root over LC, or R naught equal to root of R by G, which is equal to root of L by C. Right? So by using these two formulas we can find, see, the resistance value as R and the inductance value as L and the conductance G and the capacitance C. Generally this resistance is to be measured in ohm per meter and the inductance is to be Henry per meter and the conductance is to be measured in Siemens per meter and the capacitance to be in Farad per meter. Right? So by simplifying, if you substitute over here, means alpha value by 0.04 over here, then root over Rg. Then by equating these two, R by G equal to root Rg like that, then by simplifying these two, then all the primary constants of a transmission lines are to be obtained and all are respectively measured with respect to the per meter or per kilometer. Next, a distortionless line has Z0 equal to 60 ohm and alpha equal to 20 milli Nepper per meter, and velocity u equal to 0.6 into c, where c is the speed of light in a vacuum. Then find RLGC and lambda at 100 megahertz. F also is given, right? So as we know that alpha value is given as 20 milli Nepper per meter and velocity is given as 0.6 into c, then lambda value first we have to find. Lambda equal to 2 pi by beta, or now to find this one, we use first velocity v equal to omega by beta. So to find this beta value, beta equal to omega by velocity, we have to consider, and formula for omega is 2 pi f by velocity is given as 0.6 into c, and which is equal to 2 pi f. F value is given as 100 megahertz, 100 into 10 power 6 by 0.6 into c value is given as 3.8 into 10 power, 3 into 10 power 8 meters per second, right? So these two can be 100 into 10 power 6 becomes 10 power 8, and 10 power 8 gets cancelled, and 0.6 into 3 need to be multiplied, and it is to be considered with respect to 2 pi, then beta can be obtained in terms of radian per second. Radian per meter. Okay, then by substituting this beta value over here, then you're going to get lambda, that is wavelength, can be measured in terms of meters. This is the way we have to find lambda by using the velocity as 0.6 c. And with the help of Z0 and alpha, see, as we know that for a distortionless line, and the condition is to be RC equal to GL or G equal to RC by L, then characteristic impedance Z0 is equal to root over R by G or root over L by C. Either of the formulas we can consider, and along with that, phase constant beta equal to omega root over LC, and attenuation constant alpha equal to root RG. As we know that propagation constant gamma can be considered as root over R plus j omega L into G plus j omega C, right? So upon simplifying or separate the real and imaginary terms both sides by equating real and imaginary terms, then real term is to be obtained as alpha as root over Rg, and the characteristic impedance Z0 is to be written as root of R by G or L by C. As we know that for a distortionless line, the condition is R by G equal to L by C. Whether we have to consider in terms of for that, if you substitute over here R by G by L by C or L by C by R by G, then we are going to get all the values, all the primary constants of a transmission line are to be obtained, and resistance R is to be measured in terms of ohm per meter, and inductance can be measured in Henry per meter, and the capacitance is to be farad per meter, and conductance can be Siemens per meter or Mohs per meter, right? This is the way we have to solve. If all the primary constants are given, we need to express all the primary in terms of secondary, or all the secondary constants are given, we need to express all in terms of all secondary, then the RLGC in terms of Z0 and gamma, and Z0 and gamma in terms of RLGC are to be evaluated. And the next one is a lossless transmission line with Z0 is given as 50 ohm, is 30 meters long, and operates at 2 megahertz, and the line is terminated with a load ZL is equal to 60 plus J40 ohms. With the given here, if U equal to 0.6 into C of the line, transmission line, find the reflection coefficient, standing wave ratio, and input impedance, right? So to find a reflection coefficient, standing wave ratio, and input impedance, we need here, see, first of all, characteristic impedance is given as Z0 equal to 50 ohms, and L is equal to 30 meters long is given, and it is to be operating at the frequency of 2 megahertz, 2 into 10 per 6 hertz, and the line is terminated with load, and it is given by 60 plus J40 ohms, right? So to find the reflection coefficient, and the formula is given by gamma equal to ZL minus Z0 by ZL plus Z0. right? As we know that load impedance is given as 60 plus J40 minus Z0 is 50 by 60 plus J40 plus 50, right? So upon simplifying this one, 60 minus 50 becomes 10 plus J40 by 110 plus J40 need to be obtained as gamma. But this gamma can be written in terms of magnitude and the phase function as modulus of gamma and e power j5. So to write this gamma in terms of magnitude and the phase functions, again, if you observe here in the numerator and denominator, this is having the complex functions or looks like a rectangular form x plus iy form. To convert this rectangular form into polar, we use the formula converting this one in terms of polar form. It will be given by r1 at an angle of theta 1 in the numerator, and in the denominator r2 at an angle of theta 2 need to be obtained. By getting the magnitude of this one, we will substitute here r1 by r2 to get the value as r, and at an angle of theta 1 comma theta 2 means if you are subtracting or if you are dividing the two phase angles, we need to consider the principle as we have to subtract it one from the another. Hence, theta 1 is subtracted from theta 2 is subtracted from theta 1 to get theta. Then, this r value is to be obtained as modulus of gamma and theta to be expressed as e power j5. Our intention is to calculate magnitude of the reflection coefficient, and the range of it will be given by 0 to 1 itself. Okay, so reflection coefficient is to be ranging from 0 to 1, and the magnitude which is to be obtained by simplifying this equation to be in the range of 0 to 1 itself. Suppose if we got this gamma value to be, let it be 0.4 as its maximum, right? Gamma value to be as its maximum value as 0.4 is to be obtained. Then this is the case we have to write the standing wave ratio as, and standing wave ratio S in terms of reflection coefficient means S is equal to 1 plus modulus of gamma by 1 minus modulus of gamma, right? So 1 plus modulus of gamma means 1 plus, if you got the reflection coefficient value as in the range of 0 to 1 is to be obtained as, for example, if it has 0.4, then 1 plus 0.4 by 1 minus 0.4 need to be considered. So this will be 1.4 by 0.8 is to be obtained, means 14 by 8. By simplifying this, then we will be getting the value, means S value to be ranging from 1 to infinity, right? As we know that reflection coefficient gamma is to be ranging from 0 to 1, and the standing wave ratio is to be ranging from 1 to infinity, then in the middle values we are supposed to get as a reflection coefficient and standing wave ratio. Generally, the standing wave ratio is represented with S, and it is to be considered in terms of voltages terms only. Hence, we are representing it with VSWR, voltage standing wave ratio. Okay. Next, in order to find input impedance of a transmission line. To find the input impedance of a transmission line, we use the formula as Zin is equal to Z0 into ZL plus J Z0 tan beta L by Z0 plus J ZL tan beta L. Right? So in order to find this one, why we have considered for a lossless transmission line. Given type of transmission line is lossless one. Hence we are replacing that gamma by beta, J beta. As we know that for a lossless one, the sigma value is equal to 0. If sigma is to be assumed as 0, attenuation constant alpha to be assumed as 0. Right? So if gamma, then that gamma is to be replaced by J beta. Hence, input impedance of a lossless transmission line can be written as Zin is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So now, to simplify this, we just substitute over here Z0 by 60 plus J40 and Z0 by 50 ohms and ZL by 60 plus J40 and tan beta L. To find this tan beta L, so first L value is given as 30 meters, and to find beta, we just consider beta is equal to the formula as velocity. We can use here in order to find this phase constant, we use the velocity formula. Velocity V equal to wave velocity or phase velocity, that is given by V equal to omega by beta. From this, beta can be written as omega by velocity, which is equal to, the formula for omega is 2 pi f by velocity, as the velocity value is given as 0.6 into c. Means that 0.6 into c is the velocity of light in free space or lossless medium. Hence, it is to be written 3 into 10 power 8 meters per second. And we know that f value is given as 2 megahertz. 2 into 10 power 6 is given as the value of f. Then 2 pi into 2 into 10 power 6 by 0.6 into 3 into 10 power 8 is to be obtained as the value of beta. Right? So now, and we need to multiply these two as here 4 pi by, means its value is to be 4 pi, and 10 power 6 here, 10 power 6 gets cancelled. If it's multiplied with then it becomes a 60. 60 into 3 becomes 180. Beta value to be as 4 pi by 180 is to be obtained. And if you multiply it with L, then into 30 is to be obtained. So this 30, then 6 gets cancelled, then it will be 3. Then beta L value is to be obtained as 2 pi by 3. Right? So this need to be substituted over here. Then it becomes Z0, means first 50 into ZL as 60 plus J40 plus JZ0, means J into 50 tan 2 pi by 3 by Z0, means again 50 plus J into ZL as 60 plus J40, then tan 2 pi by 3 need to be written. Okay. Then by simplifying everything, then in the numerator we'll have some constant into plus j into some constant by some constant plus j into some constant, means real term plus imaginary term in the numerator as well as in the denominator also one complex variable need to be obtained. But here this z needs to be evaluated in terms of the complex variable like x plus iy form. To find this, or to simplify this one, we need to transform first in the numerator terms in the polar form as r1 at an angle of theta 1 by r2 at an angle of theta 2. To simplify the ratios here, r1 by r2 becomes its magnitude as r, and now to divide the angles theta 1 and theta 2, we used to consider the formula as the difference between two need to be considered, that is at an angle of theta 1 and theta 2 to be, and then finally r at an angle of theta is to be obtained is the value of Zin. But Zin input impedance of that will be expressed in form of phasor form, means some real term and imaginary term can be written. Hence again we have to transform this polar form values into rectangular form by converting the formula as Zin is equal to then some attenuation constant alpha or real term plus imaginary term must be obtained in the case of input impedance calculations of a transmission lines, and this can be measured in terms of ohms. Right? As we know that in order to find input impedance of a transmission line, we must specify whether the type of the line is a lossless type of a transmission line or lossy type transmission line. If it is lossy type transmission line, input impedance is given by here Zn is equal to Z0 into ZL plus tan H, ZL plus Z0, ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L. If gamma is exist, means it consisting of alpha plus j beta, then alpha is exist in that particular one, then the line is said to be lossy line. Hence it is the formula for the lossy transmission line input impedance, including load impedance and the characteristic impedance formulas. If it is lossless, means then alpha becomes 0, then gamma is replaced by j. Means gamma is equal to alpha plus j beta if we consider. If alpha equal to 0, then gamma becomes j beta. This is the case tan h gamma L becomes j tan beta L. Right? That's why for a lossy and a lossless transmission line, this for a lossy case tan h gamma L, and for it is lossless one, then tan h gamma L becomes j tan beta L, and hence the formula becomes here Zn is equal to Z naught into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So this is the way we have evaluated some of the parameters which are associated with the transmission lines as reflection coefficient using the formula as gamma equal to ZL minus Z0 by ZL plus Z0, and for the standing wave ratio we are representing it with S as 1 plus gamma by 1 minus gamma, and the input impedance of a lossless transmission line as this one. Right? So using all the parameters are given, there we'll solve. And here reflection coefficient gamma and the standing wave ratios are dimensionless factors. As we know that reflection coefficient is ranging from 0 to 1 and the standing wave ratio S is ranging from 1 to infinity. Right? So with this we have solved some of the problems means which are in the transmission lines. If all the primary constants are given, with the help of secondary constants, to find the secondary constant, we use all the primary constants. Then to find the secondary constants, we use all secondary constants. So resistance R, inductance L, conductance G, and the capacitance C are said to be primary constants of a transmission line, and characteristic impedance Z0 and propagation constant gamma are said to be secondary constants of a transmission lines. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.